In this presentation, we will look at some examples in which the concept of probability is applied in the biomedical field. Particularly, we will see how screening tests provide information for predicting if a patient has the suspected disease or not. Finally, we will be exploring the concepts of prevalence and incidence. And these two are very relevant to the current scenarios that the world is facing right now, as brought about by the pandemic COVID-19. So first, let's talk about the predictive values of screening tests. There are two of them. Both are applications of the concept of conditional probability. First is the predictive value positive, or PV+. Okay, so we're talking about screening tests here. So PV+ of a screening test is the probability that a person has the disease given that his screening test is positive. And this is the formula. Okay. Next, the predictive value negative of a screening test, or PV- is the probability that a person does not have the disease given that the test is also negative. And here we have the formula. So take note, the formulas follow those of conditional probability. Here, the condition being either the test positive or the test is negative. Okay? So let's apply the concept of predictive values of screening tests to a scenario we once encountered in these videos. Okay? So this was similar to what we did last time. So first scenario, 100,000 women with negative mammograms. 20 of those will have breast cancer in the next 2 years. Or the probability is 0.0002. Whereas 1 in 10 women with positive mammograms will be diagnosed with breast cancer in the next 2 years. So the question here is, what is the predictive value positive and predictive value negative for mammography? First, let's start with predictive value positive. Okay, so for the predictive value positive, take note that this is simply the probability of having breast cancer given that the mammogram is positive. Now, don't we already know that one based on the problem? We do, and it's here. So our PV plus for mammography in this scenario is 0.1. Next, let's solve for the predictive value negative of mammography. The predictive value negative for mammography will be the probability that there is no breast cancer given that the mammogram or mammography is negative. Now, we don't know this exactly, but we know a portion of it. And what is that? We know the portion where we know the probability of having breast cancer and the mammogram is negative. And we are simply going to find this. Okay? So, in predictive value negative, this is simply going to be the other percentage of this 0.0002. Okay? Or that will be 1 minus 0.0002. So if we solve this, we'll get a value of 0.9998. Okay? So, based on these results, we can see that if the mammogram is positive, there is a 10% chance of developing breast cancer for that woman. But if the mammogram is negative, that woman is good as saved from breast cancer for the next 2 years, because there is a 99.98% chance of not having breast cancer. So, the higher the predictive value of a screening test, the more valuable the test will be. So we are after screening tests that will give us a perfect 1 point for either the PV plus or the PV minus. That's the perfect test. Don't you agree? Okay. So meaning to say the test will 100% predict if you have the disease. But there is a downside to the dependence on predictive tests, no, or predictive values of screen tests. And what is that? The downside is not all patients will be able to do a screening test. And not all will want to do it. However, all patients, whether they want a screening test or not, they will always have what we call the symptom of the disease if they have the disease, right? So that's why here we are equating screening test to symptom, because if the patient does not have the screening test, the symptom is as good. Okay, so clinicians or doctors often cannot directly measure the predictive value of a symptom, but they can measure how often specific symptoms occur in diseased and normal people. So before we continue, I hope you get where we're going here. First, we started with screening tests. And in deciding for the results of screening tests, you need the PV plus or the PV minus of the tests. Now we have a problem because not everyone will get a screening test. So instead, we look at the symptom. And when we look at the symptom, we no longer go to the PV plus and minuses. Instead, we have what we call now a sensitivity and specificity of symptoms. So the sensitivity of a symptom is the probability that the symptom is present given that the person has the disease. And the specificity of a symptom is the probability that the symptom is not present given that the person does not have the disease. So if we write this in equation, sensitivity is equal to the probability that the symptom is present given that the person has the disease. And specificity is the probability that the symptom is absent given that the person also doesn't have the disease. So here's an example. So in this case, we have lung cancer. Okay. We assume that 90% of people with lung cancer and 30% of people without lung cancer are smokers. Now, in this particular problem, we are considering cigarette smoking as a symptom for lung cancer. Okay? So, how do we solve for the sensitivity and specificity of this particular symptoms, cigarette smoking? Now, before we go on to that, it's very important to group two populations here. And what are those two populations? In the first population, we have the people with lung cancer. In the second population, we have the people without lung cancer. Now, in the first population with lung cancer, how many of them are smokers? 90% of people with lung cancer are smokers. So, smokers here will be 90%. And the non-smokers will be, of course, 10% of people with cancer are non-smokers. What about people with without lung cancer? How many are smokers? 30% of people without lung cancer are smokers. So smokers here, 30% only. The other 70% are non-smokers. So how do we solve now for our sensitivity and specificity? Okay, remember, sensitivity is equal to the probability of having the symptom given that you have the disease. Which one is it here? With symptom and with disease. Exactly this 90% or 0.9. Okay? That's sensitivity. What about our specificity? Remember, specificity is the probability of not having the symptom given that there's also no disease. Now, which among these numbers is that? No symptom, meaning non-smoker, and then no disease without lung cancer. Exactly this 70%. So that's our specificity. So this is very important. Your work will be much simpler if you divide the population first into two main groups. Okay? Now we go back, we have here a term, false positive. False positive is defined as when positive test results or symptoms, okay, when the disease or condition being tested for is not actually present. Now, obviously, cigarette smoking cannot be used by itself as a screening criterion, no, for predicting lung cancer. Why? Because too many people without lung cancer, okay, are smokers. Imagine 30% of them are smokers and they don't have lung cancer. Okay? In other words, the specificity that you see here is quite low, 0.7 or 70%. So you cannot use smoking alone to predict, no? Okay, if someone has lung cancer. Here we have another example. Suppose the disease is breast cancer in women. And the symptom, so our disease is breast cancer. Our symptom is having a family history of breast cancer. So you have disease and symptom. If we assume 5% of women with breast cancer have a family history of breast cancer, but only 2% of women without breast cancer have such a history, then what will be our sensitivity and specificity? Okay. So again, let's divide the population into two groups. Those with breast cancer and those without breast cancer. Okay. For those with breast cancer, how many percent have a family history or the symptom? It's given in our problem. 5%. So 5% have family history. Remember, family history is our symptom. Okay? Therefore, the remaining 95% of those with breast cancer, can you imagine, don't have family history. What about without breast cancer? How many percent have family history? Okay, it's stated here. 2% of women without breast cancer have such history. So 2% have family history. Okay. So, therefore, how many percent do not have family history? That's 100 minus 2% or 98% don't have family history. So which one here is our specificity? Our specificity is the probability of having the symptom given that the disease is also there. So which among these groups represents our specificity? Have the symptom, probability of having the symptom given the disease is there. It's this one. So this is 0.5. That's our sensitivity. What about our specificity? Sorry, this is sensitivity. Sensitivity. Next, our specificity. How specific the symptom is. This is the probability of not having the symptom given that the disease is also not present. So which among the groups here doesn't have the disease plus doesn't have the symptom? Okay, it's this group. So this one, therefore, is 0.98. Okay, now take note here. This is even lower. This is 0.05. Take note that the sensitivity is very low. Now, because the sensitivity is very low, you cannot always rely on family history to tell if a woman will have breast cancer or not. Okay? So, we have what we call as a false negative. False negative is defined as a negative test result or symptom when there is actually really a disease present. Okay? So again, we cannot use family history. There will be a high false negative result because the sensitivity of family history as a symptom to breast cancer is very low, 5%. Now let's try this problem. So the level of prostate-specific antigen or PSA in the blood is frequently used as a screening test for prostate cancer. Okay, so you have here the data regarding the relationship between a positive PSA and prostate cancer. So, questions. What are the sensitivity, specificity, PV plus and PV minus of the test? Okay, so let's solve this one. So first, let's solve for sensitivity. Sensitivity is just the probability of having the symptom when the disease is present. Okay, so for sensitivity and specificity, we group this population or sample of people into two groups. Okay, those without the disease and those with the disease. Okay, so how many have the disease? You can see here those with prostate cancer. Okay, there. So let's start with that. So for sensitivity, probability of having the symptom and then having the disease, this will be equal to, first, the total number of people with the disease, and that's 92 plus 46. How many of them have a symptom or positive PSA test? It's this first group, 92, positive PSA tests, 92. So if we're going to divide these numbers, the answer will be 0.67. That's for our sensitivity. Next, for specificity. Specificity is the probability of not having a symptom given that there's also no disease. Now this time, let's look at the population with no disease. Let's erase this. No disease, so we have this and then this. What's the total number? That's 27 plus 72. Now, since specificity is asking for the probability of having no symptoms, which among these two doesn't have a symptom? It's this one, the 72 people, so 72. So if we compute for specificity here, the answer will be 0.73. So we're done with sensitivity and specificity. Now let's go to our predictive values. So we have a PV plus and then a PV minus. Now for the predictive value positive, that's just the probability of having the disease given that the test is positive. And then predictive value negative, that's just the probability of not having the disease when the test is negative. Now, in sensitivity and specificity, we group according to whether there's disease or no disease, right? In PV plus and PV minus, we'll group according to positive test or negative test. So let's start with PV plus. So this is simply equal to how many of those had positive tests. So let's look here. We have this group and then this group. So that's 92 plus 27. Now, how many of them have the disease? It's this group, right? So that's 92 as a numerator. So therefore, our PV plus is 0.77. Now for our predictive value negative, let's look at the total number of people with negative tests. So that's this group and then this group. That gives us 46 plus 72. How many of them doesn't have the disease? It's this group. 72 will be our numerator. So when we divide, the answer will be 0.621. And there you go. Now we've solved for the sensitivity, specificity, predictive value positive, and predictive value negative for PSA test for prostate cancer. Now here are the last two concepts. Now, application of probability in the biomedical field, the concepts of prevalence and incidence. So prevalence of a disease is the probability of currently having the disease regardless of the duration of time one has the disease. So prevalence is obtained by dividing the number of people who currently have the disease by the number of people in the study population. So here's an example. I'll just let you read through this example since it's very self-explanatory. So the answer is already given here. The prevalence is 20.3%. And here we have some numbers, some values. Then we also have incidence or cumulative incidence. The probability that a person with prior disease will develop a new case of the disease over some specified time period. And here's a sample problem. And you can see here, there's our incidence. So you might have heard of the terms incidence and prevalence. So what's the prevalence of COVID-19? What's the incidence of COVID-19? So by now, you should have an idea what those two mean, that they have something to do with probability.